Hello and welcome back. Alright, so hopefully you are all able to write a solution for your towers problem. Um, if not, never fear. I will walk you through the code, and I think you're going to be surprised. Alright, so our solve towers function looked like this. Void solve towers. We had int count. We had a character source. Character destination. And character. So your source, destination, and spare. That's an E. All right. So remember our base case. If count equaled 1, then we moved our disk from the source to our destination. All right. That's simple enough. Let's just print out a message. Let's do standard cout move disk from pole source to pole destination. All right. Otherwise, we do this. Okay, so you know what we do. We solve the n-1 problem, moving our items from the source to the spare. Okay, so that's what we do. We call solve towers count -1. We move it from the source that we were given. Now, what we want to do is, instead of moving it to the destination that we got passed in, we want the new destination to actually be that spare pole. Okay? So we do spare, and then we pass the destination. All right. So basically, remember this was solving right here. This was solving the ABC. Well, now we want the spare and the destination to be swapped. That's why we have spare and destination there. All right. So after we solved the problems above that, we know what we needed to do. We needed to move that biggest disk into the correct middle spot. Okay. So that is indeed what we will do. We know that there was only one left, and we are going to move it from the source. We are going to move it to the destination, and we're going to pass in what that spare pole is. Okay, so now you remember that when we did this, we have all of the items on the temporary spare post, post C, and you know what? We need to move all of those back so that we can move the biggest disk off the bottom into our destination. All right, so let's see how we do that. Solve towers count -1, and then we're going to move from the spare pole. Remember, that is the new source of all of our items that we moved off of the original source. Well, we need to move those to the destination. And then we pass in the spare, which is that original pole that we're on, which is the source. And believe it or not, if you put that in your little compiler, you run that code, this is your solution. So let's go ahead and take a look at what's happening. So let's do that n equals 1 case. All right, let's go ahead and I'm going to create a new layer and hide this for a minute. Okay, and we'll just jump back and forth between those. Okay, so let's draw out our poll. And let's figure out what is going on and why this is actually working. Okay, so here's our code. Our code says if count equals 1, well, let's look and see what our first call looks like. Okay, so this puzzle looks like this. So our initial call is solve towers, and it's count of 1, A, B, and C. Okay, so the message we're going to get is move disk from pole A to pole B. Perfect. Let's make sure our code says that. Our code says move disk from pole A, our source, to pole B, our destination. And that's in fact what happens. Our count is 1. Okay, so what happens when our puzzle is a little more complicated? Okay, my pen is acting funny. Oh, maybe it helps if I draw on the correct layer. Okay, so we have our pole. We have A, B, and C. And we have 2 disks. All right. So our initial call looks like this. Solve towers to A, B, and C. All right. So let's look what happens inside of our code now. All right. So count obviously does not equal 1. So you know what? We need to make a call to solve towers. And the count is going to be, or the count minus 1, source, spare, and destination. All right. So over here, what we have is we get this call. We'll get solve towers, and we get 1. We get A is our source, C is our destination, and B is our spare. And let's see if that actually looks like what happens. Well, you know what? We know that we need to move this small disk over to C. Well, what happens? This is 1. So we know that based on our code, we're going to move the pole. So this says we're going to move the disk from pole A, which is our source, to pole C, which is our destination. And you can see that's exactly what these parameters say. All right, so this call right here, we'll call it a little 1. So we know that that is 1. All right, so now what happens? Our code stops on that move pole. Perfect. So now we have this call right here. And this is solve towers 1, source, destination, spare. Okay, so then we get this one. We get solve towers 1, A, B, and C. So what this is going to say, it's going to say move disk from pole A, which is this big one, to pole B. And we'll call this 2. And so we know that our second move is indeed that one. So we know that we have more problems to solve because we still have disks left on C. Our code says, you know what? We need to move all of those disks from disk C over to our destination. So our source is our spare. So let's look and see what that call is going to look like. So we have solve towers 1, our source, our destination, and our spare. Source, destination, spare. Perfect. Okay. So if we go ahead and take a look at this, this is going to say move disk from pole C to pole B, and that's in fact what our third move will have to be. Now you can step through this for n equals 3. You're going to get a lot more function calls, and you're going to see a lot of calls that, right here, you're going to get a lot more calls under this layer because you're going to get 3 extra calls there. And then you're also going to get, you'll get the same 1 call here, but then here, you'll get a lot more calls because your count is bigger than 1. So when it's 3, you're going to have to go to 2. And then 2 is going to need to make all these calls right here. It's going to make all these same calls. And then you're going to go down to 1, and then 1 is your base case. So that's really the solution to the Towers of Hanoi problem. I hope that made sense, and when we walked through, that actually, kind of made sense what was going on. We were moving n minus 1 disks from pole 1 over to our temporary space so that we can move that big disk to the middle. And that's what the second step of our code is. Move that big disk to the middle. And then our very last line of code is, you know what? We need to move all of those disks from C over to pole B in the middle. But in the course of doing that, we're going to have to use some temporary spaces, and it's going to go through and run through this code and essentially solve the same problem each time over and over again, just in small little steps. And that really is the heart of recursion. So this problem is probably going to take you a little bit more just kind of fiddling around to understand it. Sometimes recursion can be tough, and sometimes you just need to think about it in the right way to make it click for you. So some other practice problems you can do with recursion if you're having problems, you can make a countdown. How do you actually print out a countdown from 10 using recursion? So instead of doing a for loop, how would you do that doing recursion? Or how do you take a string and print out the characters backwards? So those are some good practice problems that you can do with recursion. So with that, I'm just going to go ahead and wrap up this video. Thanks.